I am Nand Kishore. Our group is working on biothermodynamics and biophysical chemistry of biologically important systems. We are applying a combination of calorimetric and spectroscopic techniques in understanding the problems of biological interest. Understanding the protein folding problem is a challenge, and it is important to understand the intermediates during protein folding both qualitatively and quantitatively. Our group has focused on the characterization and thermodynamic properties of these intermediates. We have also focused on understanding the protein-solvent interactions and the interactions of the building blocks of proteins with the solvent environment. In addition to its fundamental interests, an understanding of protein-solvent interactions is of considerable importance in the development of biotechnologies and industrial processes that make use of proteins. For example, in the application of enzymes in organic solvents and the use of immobilized proteins in chemical separation and the development or strategies for the purification and storage of proteins, as well as in food processing and preservation. Another area of interest in our lab is to understand the physical chemistry underlying the drug-protein interactions and drug-DNA interactions. Besides this, we are also working on understanding the thermodynamics and mechanism of prevention of protein aggregation and fibrillation by potential inhibitors. Identifying the groups responsible for interactions based on the thermodynamic properties is essential in providing guidelines to synthetic chemists in the design and synthesis of target organometallics.
I am Professor S.N. Datta of Chemistry Department. I joined here in 1978. In our lab, we are always working in the frontier of theoretical chemistry. Our work is on diversified topics, but these are all new theories bringing out new concepts and new results. Our strength lies in theory and computation, backed by more than 100 original publications and 3 books. Our achievements have been introduction of theories, methodologies and concepts like relativistic Hamiltonian, min-max principle, accurate Magnon formalism, spin alternation rule, unified kinetics for growth of glucose equivalents, predictions of a large number of ferromagnetic and photomagnetic molecules. Our investigations span an abstract theme, that is relativistic theory of electronic structure, an all temperature Magnon theory of ferromagnetism, an applied theme, the rate of growth of green plants. Work in this line is expected to aid in increased food production. Another applied theme, structure and reactivity of complex biomolecules involved in photosynthesis. A recent theme of nanoscience, theory and computations on magnetic molecules, which will eventually make organic ferromagnets, spintronics and photomagnets a reality.
Hi, I am Ali Contractor, Department of Chemistry, IIT Bombay. My area of expertise is electrochemistry, and so my research centers around various topics related to electrochemistry. One of the areas in which I have been working for a long time is development of sensors based on conducting polymers, chemical sensors as well as biosensors. Another area which is of interest to me is to use electrochemical concepts and techniques to develop interconnects for semiconductor devices, and also to look at new energy storage systems, essentially making use of electrochemical concepts. Some of this work has also resulted in technology which is being commercialized by a startup company at IIT Bombay called Polymeric Sensors, which is being incubated at SINE. The launch product of the company is Polysense Aqua, which is meant to test drinking water for potability using set of sensors and electronics requiring minimal intervention from the user. We hope to develop similar products for other areas such as soil testing, milk, and so on.
I am Bhalchandra Tembe from the Department of Chemistry, IIT Bombay. My research area is in theoretical chemistry. In particular, we are interested in the solvations of ions, ion pairs, and different reactions in solution media. Let us consider the solvation of a single ion here. When an ion is solvated in water or other solvent, the solvent molecules surround this ion, stabilizing the ion. So, instead of an ion, suppose now I have an ion pair. The ion pair normally exists as a contact ion pair in the gas phase. If I have it in a solution, there is not only a contact ion pair, but also a solvent separated ion pair like this. So, then we can now consider the reaction between a solvent separated ion pair and a contact ion pair. So, and how different solvents stabilize the contact as well as the solvent separated ion pair. We have considered water DMSO mixture as the solvent, and we consider the solvation in different compositions of these mixtures. The same methods that we use to calculate the potentials of mean force in solution can also be used in studying reactions such as the solvolysis of a Norbornyl species. Now, this is a Norbornyl species where a reaction such as removing this particular leaving group from here. So, this is an exo-leaving group, this is an endo-leaving group. It is found that the exo-leaving group leaves much faster than the endo, and the rate difference being thousands of times more than the endo-leaving group. So, we use the same methods of molecular dynamics to study the dissociation of exo versus endo in various solvent mixtures. So, using these simulations, we hope to find out what is the difference in the free energy of solvation for the exo versus the endo in the transition state. So, this is the second kind of a problem we are studying. The third kind of a problem, suppose I have an oscillator which is immersed in a solvent. So, the oscillations are all quantum mechanical in nature, whereas the solvation can be studied using classical equations of motion. So, we study the solvation of an oscillator again in different solvents, solvents with different dielectric constant, different dipole moment, different density. So, we wish to study the effect of solvation on vibrational motion of different types of molecules. Another area that we are involved in is creation of several books on an NPTEL project. So, here we use computer aided design such as Java applets, animation and things like that to create teaching material for various students all across the country. So, NPTEL has created several books in several fields. So, we are interested mainly in physical chemistry, experimental physical chemistry, statistical mechanics, thermodynamics, computational chemistry and so on. Thank you.
Hello, I am Professor Shashidhar in Department of Chemistry. Ours is a protein folding and dynamics lab. We use molecular dynamics simulations to understand structure, dynamics and function of proteins. The mechanism by which an unfolded protein folds to its functional 3D structure is known as protein folding. Understanding this is important in view of its importance for medicine and biotechnology. Since early folding events play a crucial role in the folding of a protein, in our lab we model events like formation of turns, loops and beta hairpin structures starting from unfolded states. Conformational changes underlie many biological phenomena, and such conformational changes are coded in the dynamics of proteins. We model such conformational changes and protein dynamics with molecular dynamics simulations using protein and peptide models. Now I shall give some examples of what we are doing. We recently modeled beta hairpin folding using a peptide model from staphylococcal nucleus and found that turn formation and hydrophobic interactions play an important role. We also found reversible alpha helical to beta hairpin transitions in a peptide from glyceraldehyde 3-phosphate dehydrogenase. Understanding such structural ambivalence is important in learning more about conformational diseases. Currently, we are working on thermodynamics of turn formation, rollout dynamics in Gal-1P protein, and understanding allostery in a protein model.
I am Anindya Datta, Department of Chemistry. In our Ultrafast dynamics group, we try to study the excited state dynamics of many chemical and biological processes in the nanosecond to femtosecond time regime. The question that I am frequently asked is, what is it that can happen in such a short time? A lot of things can happen actually, the most fundamental of them being the breaking of a chemical bond. And many such photoprocesses which take place in this time regime are most important and happen all around us all the time. Two common examples are the process of fission and photosynthesis. In our group, the technique that we use to study these dynamics is fluorescence spectroscopy. The two tools of trade that we use are time correlated single photon counting and femtosecond fluorescence upconversion. We have studied many fluorescent organic molecules, starting from potential drugs for anti-cancer photodynamic therapy to novel protein stains prepared in a University of Australia. More recently, we have gotten into applications of ultrafast processes in materials science. The two materials that we are working on at the moment are silica nanostructures and the Nafion membrane, which is a polyelectrolyte membrane used in fuel cells. The interest in silica nanostructures usually stems from the fact that they are potential drug delivery vehicles. However, we are trying to probe a very different aspect of it, and this aspect is photoluminescence. Silica nanostructures have blue photoluminescence. They give out blue light when they are excited by, say, ultraviolet light. We are trying to find the origin of this phenomenon. Moreover, we believe that these silica nanostructures can be very efficient scaffolds for light harvesting nanoantennae. That is the dream project that we have currently embarked on. The second material that we have been studying is Nafion, as I said. And Nafion, what happens is that it is a membrane which takes up protons or any other cation, but it does not allow negatively charged ions to go through. The dynamics of hydrogen ions is something that is still not understood all that well. Many people have tried to use different techniques to understand the dynamics of hydronium ions and water molecules in Nafion. We are trying to use the technique of fluorescence spectroscopy to understand it.
My name is Dr. Arindam Chaudhary. I am an assistant professor in the chemistry department at IIT Bombay. I work in the field of experimental physical chemistry, but of late my focus has been working in microscopy, or more specifically single molecule fluorescence and single particle fluorescence microscopy. My lab here constitutes of a small synthetic lab where we make some of the molecules and purify some of the materials that we need. And most of these fluorescent materials are looked at through the microscope is equipped with a laser and a CCD camera, and we have actually developed this microscope. So our job is not only about getting something and just collecting data, analyzing it and producing something. It's more about actually developing new techniques to look at something very interesting. We are specifically looking at 3 projects at this moment, and one of them involved diffusion, that involves rotational as well as translational diffusion of small probe molecules like rhodamine 6G dyes as well as quantum dots in polymer thin films. The other projects involved looking at doped nanocrystals, in which and doped nanocrystals as well as core shell structures of nanocrystals, with which we look at, we can do spectroscopy or single particle spectroscopy of these nanocrystals, and we look at their behaviors in the condensed phase, either on a glass slide or on a polymer matrix. My other project that I'm really interested in at this moment involves in looking at this quantum heterostructures, which are called quantum wells, and we are investigating localized emission features that are present in these quantum wells, which are commonly used in light emitting diodes.
I am Professor Ruchi Anand, and I am at the Department of Chemistry at IIT Bombay. The major area of our research is protein X-ray crystallography and protein chemistry. And we use the three-dimensional structure, which helps us understand the mechanism of catalysis in enzymes, structure-activity relationship in many cases, and protein-protein interactions in enzyme systems. Trying to study the three-dimensional structure by X-ray crystallography, we are able to visualize what the protein looks like, and that helps us to understand how enzymes catalyzing reactions as well as conformational changes associated with it. And then we can further go on to rationally engineer or design ligands to for structure-based drug design and can be of therapeutic importance. In our lab, we have two major areas of research. One is on DNA binding proteins, and the other one is on stress signaling and apoptosis, which is cell death. In the first area of DNA binding proteins, we concentrate on two major problems, and we are trying to understand how protein-DNA interactions regulate function. In this case, we are trying to understand the mechanism of aging. In addition, we are working on DNA binding proteins which are called transcription factors, and these transcription factors play a major role in controlling antibiotic production and quorum sensing in streptomyces. On the front of protein kinases, we are working on trying to understand how these protein kinases are regulated and what are the binding partners and how protein-protein interactions with these binding partners influence function. The two protein kinases we are interested in working are involved in breast cancer and cardiomyopathy, which is heart-related disease. Developing inhibitors for these kinases can be of extreme importance, and so as a part of our work, we are also trying to stress on structure-based drug design work which is relevant to these kinases in addition to understanding their function.
I am Professor H.B. Singh in Department of Chemistry. Our broad area of research is on organometallic chemistry of main group elements, in particular selenium, tellurium and mercury. The work involves a combination of synthesis and characterization of novel and interesting compounds, and these compounds have applications in the area of organic synthesis and as models of selenoenzymes.
Pradeep Mathur, Chemistry Department at IIT Bombay. My area of work is in organometallic chemistry. I do synthesis, reactivity studies and structural characterization by X-ray crystallography. The synthesis work essentially involves developing new facile methods for mixed metal clusters. Here we have used the approach of using single atoms as ligands derived from the main groups of the periodic table. These act as very convenient bridges and stabilizers for holding different types of metal carbonyl units together to give us new forms of metal clusters. Since we adopt very mild facile reaction conditions, we have been able to generate quite a few interesting clusters which show novel reactivity features. In our reactivity studies, we have essentially looked at acetylenic bonds. So, we have been able to activate the acetylenes and diacetylenes. We have also looked at carbon-carbon bond formation reactions on our organometallic complexes, including our cluster compounds. We have also looked at formation of new heterocyclic compounds, both with nitrogen as well as the chalcogen containing ring systems. And lately, we have discovered that very often, in fact, one doesn't require clusters for getting novel catalytic and organic activation reactions. As a surprising result, we have in the last couple of years discovered that simple iron carbonyl can act as a catalyst to give us very, very interesting and new organic reactions and organic activations. Of course, all of this work is complemented by very dedicated X-ray crystallographic studies, and this is done in collaboration with the National Single Crystal X-ray Diffraction Facility, which we in IIT Bombay are very fortunate to have. In the crystallography unit, we have also looked at single crystal to single crystal transformation, and these are ongoing studies, and we continue with that particular work. So, in essence, we do synthesis, we do structure studies, we do a little bit of catalysis, and basically organic activations on organometallic compounds.
My name is C.P. Rao. I am from the Department of Chemistry. Our group is mainly involved in working on aspects of bioinorganic chemistry, which is nothing but inorganic chemistry of the biological aspects. We are at the interface of chemistry, biology, materials. Our group uses a number of small molecular systems, large molecular systems, both by experimental as well as the computational methods. And we use a lot of synthetic, organic, inorganic synthetic methodologies. We also use a lot of analytical spectral techniques, and we also use microscopy techniques in our research. We do isolate our own protein systems, biochemistry aspects, biophysical aspects, and biological aspects as well. A lot of structural work also goes on besides the spectroscopy. We do work on the microscopy aspects of both small molecular systems as well as the large molecular systems, both. We develop our own small molecular systems to utilize these into these biomolecular aspects of it, and thus we generate a plethora of data that explains bioinorganic aspects at large through our own small molecular chemistry. They act as models. They also provide a lot of small molecular systems which are of great use in later on as materials and glycotargeting aspects. We have been working on aspects related to the cytotoxicity of a number of metal complexes that we develop using molecular systems like glycoconjugates. And glycoconjugates and calixarenes act as our platform systems for all our studies. So, our work is at the interface of chemistry, biology and materials. In this process, when we use small molecular systems, we are able to get a lot of sensor systems, and it becomes an additional activity that goes on in our group while supporting the main activity, which is biological inorganic chemistry. And we also have been working on glycotargeting in terms of the glycobiological, which will be of use in disease diagnosis and therapy. So, overall our efforts, we would like to approach towards the materials and towards the drugs for anti-cancer agents, other kinds of for diseases as well, and including disease diagnosis and therapy aspects.
I am Professor G.K. Lahiri, Department of Chemistry, IIT Bombay. I have been here since 1993, so last 17-18 years. My group at IIT Bombay, they are trying to carry out several fundamental as well as application aspects of inorganic chemistry. We are primarily working under the purview of coordination chemistry, dealing with the transition metal elements and their fundamental aspects. So, primarily we are trying to understand three different processes. Firstly, we are trying to understand the valence and spin interaction at the interface of redox non-innocent metal ligand setup. We are just trying to understand using different experimental as well as different theoretical events to the valence and spin state interaction at the redox non-innocent metal ligand interface, and also we are trying to understand the intermetallic electronic coupling between the metal centers via the bridging organic ligand systems. So we are essentially trying to understand how the electron is getting flowing across the metal ligand metal setup, and this particular understanding would facilitate to develop the molecular electronic devices as well as different optical devices. We are essentially not trying to develop any devices, but we are trying to develop the understanding which could eventually be extended towards the designing of such optical or molecular electronic devices. We are also trying to look into the application potential of different metal complexes as well as metal clusters towards their catalytic activities. So we are also carrying out the catalytic activities both at the homogeneous as well as the heterogeneous interface, and we try to see that how our catalyst can effectively carry out different organic reactions which are industrially as well as commercially viable. So far we could make substantial progress towards the topics what I have covered so far. However, we are still in the process to develop much more efficient system.
Welcome to the Phosphorus laboratory, the research group of Professor M.S. Balakrishna in the Department of Chemistry at IIT Bombay. Our research has three main objectives. One is ligand synthesis and the main group chemistry. The second one is coordination chemistry and transition metal organometallic chemistry. The third one involves the utility of these compounds in homogeneous catalysis and medicinal applications. We design phosphorus-based ligands which are nothing but an assembly of electronically and sterically tuned donor groups containing at least one trivalent phosphorus atom. Once after making these compounds, we would try to explore their transition metal chemistry, and that decides about their possible utility in applications such as homogeneous catalysis and medicinal and biological studies. So now I would like to show you a slide. So this slide gives the glimpse of the research activities that are going on in our laboratory. So as I mentioned, we are the inorganic synthetic groups. Okay, we make novel ligands and study their coordination chemistry, and in that process we choose some of the ligands that we find suitable for catalysis. We employ them in catalytic reactions such as carbon-carbon coupling reactions, carbon-hydrogen coupling reactions, hydroformylation and carbonylation reactions, and also polymerization reactions. And then in this process we are also making metal bound supramolecular compounds and also coordination polymers and metallo-macrocycles. And some of these phosphorus bound copper 2 and gold compounds are found to be very good reagents in anti-tumor activity, especially for cervical cancer and breast cancer in human beings.
I am Murugavel. I am Professor of Inorganic Chemistry at IIT Bombay. Everything what we do in our laboratory involves the broad area of main group organometallic chemistry, which of course is a very classical field in chemistry. However, we try and tackle some very modern and contemporary problems within the realm of this main group organometallic chemistry, so that we can contribute to modern advances in both inorganic chemistry as well as chemistry of materials. For example, we use this main group chemistry as a tool to devise rational routes to make highly porous materials in a stepwise manner. Classically, people make zeolites using high temperature, high pressure, too many days of reaction time. what we do is, we use the fundamental principles of main group chemistry to assemble, building blocks, from primary building blocks to secondary building blocks to tertiary, and put them all together, in one flask and just shake it up for a few minutes at normal temperature, normal pressure, and produce zeolites. And not only, this preparation of these porous solids is the outcome of our research in main group chemistry, we also use this, broad area to make new precursors for materials. For example, to make fine particle metal oxides, metal sulfates, metal phosphates, and metal silicates, we make precursors which are highly volatile and try and decompose them at temperatures as low as about 150 degree to 200 degrees centigrade and make these fine particle materials. And we also use these principles to make what are presently known as metal organic frameworks, coordination organic frameworks or covalently linked organic frameworks, with the hope that we would also be contributing to some applied areas of chemistry, namely storage materials, gas absorption materials, molecular sieves, and so on and so forth.
I am Professor Ravikant from Department of Chemistry. My research field is bioinorganic chemistry, where we work on systems which are related to biology. So our main topics are mainly the synthesis of macrocycles, that includes porphyrins and related macrocycles. Now, porphyrins are very important biomolecules present at the active site of several biomolecules such as hemoglobin, and it is a very important myoglobin, cytochromes, and also in the cytochromes and also in the photosynthesis. So our main aim is to synthesize these molecules in the laboratory and develop a methodology and study the energy transfer process, which is a key process occurring at the natural photosynthesis. In addition to this kind of things, we also work on dyes. There also the main aim is to synthesize boron dipyromethane based dyes and use them for various other applications and so on.
I am Prasenjit Ghosh at Department of Chemistry, IIT Bombay. I work in the area of organometallic synthesis and homogeneous catalysis. The main focus of our work is on synthesizing metal complexes with important catalytic property. For catalytic property, I mean we work in making molecules which make chemical transformations easier, more efficiently, and with greater purpose. We make metal complexes that catalyze various carbon-carbon, carbon-hydrogen, and carbon-nitrogen bond-forming reactions. These reactions are of importance to organic chemistry in particular because of their very high synthetic values, particularly in pharmaceutical as well as chemical industries. We design several transition metal complexes for this purpose and study their catalytic property. Beyond catalysis, we also study their biomedical application properties, particularly with respect to their use as anti-cancer and antimicrobial activity. In short, my group deals with designing transition metal complexes, synthesizing them, and studying their catalytic properties as well as biomedical properties using many sophisticated instrumentation techniques and various chemical characterization methods that are available in literature.
I am Professor Rajaraman, joined in this department a year back in the Inorganic Chemistry division. So here we have a different interest. One focuses on molecular magnetism, where we are starting with 3D 4F complexes, where transition metal, mixture of transition metal lanthanide complexes, where we are focusing on calculating the exchange interaction on isotopic as well as the anisotropic complexes, and then other interest is on understanding the reaction mechanism of different transition metal mediated catalytic reaction, and a couple of MSc students are working on this aspects, and we are also just starting to do something on surface chemistry, basically trying to understand the property of single molecule magnets and magnetic property of single molecule magnets on the surfaces. And other interests are basically on EPR spectroscopy, which is also just exploring EPR spectroscopy of matrix clusters and radical intermediates, those sort of stuff.
I am Devabrata Maiti, new faculty in this chemistry department. I am very proud to be a part of this prestigious place. My research group will focus on identification of the unsolved chemical issues, and we will work towards providing first-hand solution to such issues. We are interested mainly in the research area of organic and inorganic chemistry. So my research group will work basically in the interface of these two fields. More specifically, we are interested in the development of transition metal mediated reactions and in bio-inspired catalysis.
I am Vishwakarma Singh, Professor of Chemistry in IIT Bombay. We have been working in the area of organic synthesis, especially in the development of synthesis of bioactive molecules that are derived from humulene cyclization cascade. Our main objective has been towards synthesis of polyquinone natural products, those belonging to sesquiterpenes, protoeludanes and marasmane, a class of natural products. And this methodology involves the creation of reactive species from simple aromatic starting materials into a highly reactive species called cyclohexa 2,4-dinones, followed by their interception with the reactive pi-4 partners and subsequently reactivity modulation of the resulting adducts in ground and excited states. Thus, we have completed synthesis of several natural products. Recently, we have also developed a synthesis of broad-range antibiotic molecule known as platensine from simple starting material as 3-methyl-saligenine.
I am Sushil Durrani. I am a professor in the Department of Chemistry. My lab essentially works on the interface between chemistry and biology. Our primary interests are in protein structure. Our interest basically is to understand how proteins fold and how they work to perform their functions. And in this, my lab basically adopts what I would call as a synthetic approach. We do not focus so much on the actual proteins of nature, but we model them in the lab by synthesizing small segments of proteins as polypeptide structures so that we can perform experimental characterization of these structures, and also we can perform theoretical studies, we can perform computational studies of these structures, so that by the combined input of theory and experiment, we can get fundamental insights about how these structures actually perform their functions, how they fold and how they act as enzymes. So, the ability to basically apply theory as well as experiment together is what is unique in the researches that I perform in my lab. And the interest in the long term is to basically not only understand the basic question of how proteins fold and function, but also to target, first of all, proteins for design and discovery of drugs. And the second possibility is that by designing synthetic constructs which look like proteins, we aim to basically make artificial molecules which will display protein-like properties. So we try to basically synthesize polypeptide structures that will fold and act like enzymes.
I am Professor A.K. Singh of the Department of Chemistry. I work in the area of biomolecular chemistry. A number of projects are going on in our lab. One of the main projects that we are interested in deals with photo control of the structure and functions of biomolecules. For example, we are interested in chemistry of vision, various photobiological processes that occur in the nature. To solve these problems, we make use of organic chemistry, bioorganic chemistry, and other tools and techniques of chemical sciences. The second project that we are interested in is on biomolecular caging, in which we make a biologically active molecule inactive and then make it active by photolysis. This technique has various applications in medicine, materials, physiology, and in a other number of areas. The third project that we are working on deals with excited state chemistry of organic molecules, particularly linear polyenes like vitamin A aldehyde and related molecules. Dealing with the excited states of the molecule, we have also developed and designed a number of fluorescence probes which have applications as diagnostics. We are also interested in designing and synthesizing nanoparticles of organic compounds which have therapeutic as well as optoelectronic applications. Besides, we work in a number of other small projects dealing mainly with structure, function, synthesis, characterization of organic compounds, both active as well as inactive.
My name is Sambasivarao Kotha. Our research group works on synthetic methodology. Mainly we work unusual amino acid synthesis, design, peptide modifications. Metathesis is the topic that was given Nobel Prize in 2005, and Suji coupling also given Nobel Prize in 2010. Our major achievement is, in the last 9 years or 8 years, most of our papers are either most downloaded or most cited papers, and our group actively works in designing new molecules.
So I am Professor Krishna Kaliyappan from Department of Chemistry. My research work is organic synthesis and chemical biology. We have been working on total synthesis of natural products and natural product-like molecules. In natural products, we focus mainly on developing new strategies for antibiotics and anti-cancer compounds, and we have synthesized a range of angocyclone antibiotics, and some of them show significant activity and selectivity against Helicobacter pylori, which is responsible for ulcer. And we also synthesized a couple of interesting antibiotics, platensimycin and platensine, which are supposed to be the most potent antibiotics known in the history so far. And in anti-cancer compounds, we are working on total synthesis of Taxol, erythrobin, epothelons, discodermalide, and dictyostatin. Recently, we completed the total synthesis of palmolide A, which is a marine natural product isolated from Antarctic Ocean. We are also working on several other related anti-cancer compounds like calistatin, leptomycins, etc. In addition, as I mentioned, we are also working on developing new strategies for synthesis of natural product-like molecules, particularly hybrid natural products. In hybrid natural products, we have synthesized sugar oxosteroid quinone hybrids, and we also synthesize several C-aryl glycosides and Spiro C-aryl glycosides. We also develop interesting strategies for the synthesis of oxa and aza sugars, particularly bridged oxa and aza polycycletols. We also recently developed some new strategies for synthesis of beta-lactam antibiotics using Kinikosa reaction. And more importantly, our main objective has been to train our undergraduate and graduate students in organic synthesis.
I am Professor N.N. Nambudiri from Department of Chemistry, IIT Bombay. We work in the general area of organic synthesis and physical organic chemistry, especially mechanistic organic chemistry. The substrates of our interest are nitro compounds and polycyclic cage systems. Using nitro alkenes as the key substrates, we develop novel methodologies involving one-pot multi-step, multi-component and atom economical reactions, many of them under organocatalytic conditions. So these methodologies allow us to synthesize novel multifunctional molecules that are of interest to biology, medicine and material science. And using polycyclic cage compounds, we develop novel high energy density materials that have applications in a volume limited environment. We also pursue development of novel chiral templates using polycyclic cage systems that can be used as ligands and catalysts in asymmetric synthesis.
Myself, Anil Kumar, Chemistry Department, IIT Bombay, Mumbai. We are synthetic polymer chemists, and our lab is looking into various designs and strategies to design next generation of semiconducting materials based on polythiophene. Here the main effort is to come out with new synthetic strategies by which we can get soluble, high quality, which we call the device quality polythiophene based semiconductors. The idea is to introduce air stability in polythiophene, make them N-dopable and P-dopable, along with increasing the charge mobility in these materials. Once we get these materials which have these properties, then we look into these application into electronic devices. The type of devices which we explore are the thin film transistors, chemical and biological sensors, transparent conducting coatings. In the case of chemical sensors, we have now developed materials which can detect various explosives at room temperature. In fact, these are the few rare materials which do detect explosives at room temperature. Then we join hand with a private company in Bangalore called Big Tech Labs, and we finally have developed a handheld device which is fully automatic, battery operated, which can detect various explosives at room temperature. The device is in the final stages, and hopefully the device will be launched in the middle of 2010 for commercial use. Once this technology is developed, now we are designing new materials which then can be used for other chemical sensings like alcohol or substance abuse, etc. Along with this, we'll also look into graphene structures, where the idea is to incorporate graphene into polythiophenes and then see if we can improve the transparency while retaining the high conductivity. Once we have these coatings which are highly transparent and highly conducting, then these will have large application in the flexible display devices where the front electrode has to be transparent. So we basically explore our synthetic skills in designing of the new materials which should be printable and useful for organic electronics.
I am Raghavan B. Sunod. I work in organic division of this department. My research interest is primarily in the area of computational chemistry with specific emphasis towards understanding organic reaction and reaction mechanism. In particular, we are interested in understanding stereoselectivity process, stereoinduction, role of explicit solvents in chemical reactions. We use a variety of modeling tools with
the help of DFT and ab initio methods to understand transition states for chemical reactions, particularly the carbon-carbon bond formation reaction, which control the stereochemical outcome of many interesting asymmetric reactions. The approach would typically involve finding transition states and connecting it with various intermediates and possible minima and maxima, and this would help us understand the kinetic and thermodynamic features of chemical reactions, and in the long run we would also like to design new catalysts with the help of computational methods, and some of our catalysts has already been tested experimentally. So we work in a variety of themes: organocatalysis, transition metal mediated organic reactions, CH activations, which are of high significance in industry as well. Apart from this, we are interested in understanding weak molecular interactions, which constitute a variety of aggregation phenomena in chemical sciences. We are interested in quantifying these interactions using ab initio and DFT methods.
I am Professor Rodney A. Fernandez, working in the Department of Chemistry, IIT Bombay. I basically work in the area of asymmetric synthesis of natural products, also work in the total synthesis of natural products, and we also develop methodologies, special emphasis on chiral catalysis. So we have also worked on synthesis of chiral catalysts and use them in chiral catalysis, developing new reactions, asymmetric reactions. I have a group of around 8 students which are registered for PhD, and also 5 project students which are either MSc students or working on projects. We have recently completed the synthesis of cephalosporolide. We have also completed the total synthesis of cardinalin 3. We are also working on many of the other important bioactive natural products. We have also been working on development of chiral palladium catalysis. We have developed 2 chiral palladium catalysts, and we have been trying to see if they can enhance our asymmetric synthesis methodologies. Our students are working on various topics of chemistry like synthesis, asymmetric synthesis, total synthesis, natural product synthesis, methodology development, and we have projects funding from different agencies funded from from the government of India. And then I have also been involved in teaching, basically for the PhD students and also for the 2-year MSc students.
I am Pradeep Kumar. The major research focus of our lab is the chemical biology aspects of nucleic acids. We are trying to expand chemists' toolbox to develop viable nucleic acid based therapeutics. We are synthesizing and evaluating chemically modified interfering RNAs, messenger RNA cleaving DNA enzymes, and molecules which can target quadruplex forming nucleic acids. We use a multidisciplinary approach employing techniques from organic chemistry, computational chemistry, biochemistry, and cell biology.
I am Dr. Suvan Kulkarni from Department of Chemistry at IIT Bombay. We work in the area of carbohydrate synthesis. Carbohydrates in the form of glycoconjugates and oligosaccharides are ubiquitously distributed on the cell surface, where they are involved in numerous vital life processes such as viral and bacterial infections, cell growth and proliferation, cell-cell communication, and immunoresponse, and are thus implicated in various diseases. In order to study the biology of these glycans, chemically pure and structurally well-defined compounds are essential. However, these carbohydrates, being present in microheterogeneous forms, could not be isolated in acceptable purity and amounts from natural sources. Thus, chemical synthesis of glycans offers a viable solution to this problem. We are mainly interested in the antigenic oligosaccharides and glycolipids specifically expressed in infectious diseases such as tuberculosis, AIDS, malaria, and stomach infections, as well as cancer. As a first step towards understanding the molecular level details of these interactions and study the carbohydrate recognition in various diseases, we are devising newer ways to chemically synthesize the glycolipids, glycoproteins, oligosaccharides, and C-glycoside analogues of carbohydrate antigens.